It is section 6.4, areas of surfaces of revolution. Let's begin with a formula for curved surface area of Frustum. If a cone is cut by a plane parallel to the base, then we can get a Frustum. This portion is rotated, then we can get this Frustum. We have to find the curved surface area of the Frustum. In order to do that, let's go back to this picture. This length is little l, that is now capital L, and capital R is the radius, and little r is the radius here. If we consider the triangle, the right triangle, then here this whole length divided by this portion is the same as here this radius divided by this radius. So that is exactly this equation. From this one, we can get capital L plus L by multiplying little l. And also we can solve the equation for small l to get the second equation. Now, the curved surface area of the Frustum is the same as this full cone surface area minus the surface area of the small cone cut out. Now, here the formula is given in this way. Now, once it is cut, then it becomes a sector. So in high school, you learned this one. In general, once a sector is given n, in a high school, you used to hear notation R, radius and sector length L. Then the area of the sector is same as half times RL. You learned this one. So for this full cone, and half times that is radius, capital L plus L, and once it's cut, then that will be the arc of the sector. So that length must be 2 pi capital R. So we have this one. For this small cone, now that is radius, and the sector length is 2 pi real r. So we have that. Now, by using equations 1 and 2, and we can simplify this term into that form. Now, so we can write in this way. The first term surface area, there's 2 pi, and that is average radius, capital R plus R divided by 2, and L is side length here. So that 2 pi average radius and that length. So that is the curved surface area of the Frustum. Okay, now we'll go back to our main subject for the section, the surface area for revolution. Now we start with the rotation is about the x-axis. We start with a curve y equal fx defined over a to b. Now we rotate it about x-axis. Then this curve will make a surface, and we'll try to get the surface area. And now we'll use the same technique, partitioning, approximation, Riemann sum, and their limit. So we'll use the same technique. So we start with now partitioning. The interval a to b is partitioned into n subintervals. Now for each subinterval, this arc PQ will make now here a band. now finding area of a band is not simple. For example, this is now original curve, and once it is rotated, then it will make a band. But area of band is not easy to get. So rather than this curve, we'll try to make a straight line segment, and that is rotated. Then it will make a frustum. So the area of a band will be approximated by the area of this frustum. Okay, that is approximation. Now, already we know that the area of the frustum is now 2 pi average height. So xk minus 1 to xk, so that this one is f at xk minus 1. And radius over here is f over xk. So average radius, and now the length, by using Pythagorean theorem, we can easily see that that is now the length. Okay, so that is now the kth frustum surface area. We sum them, but before summing, this portion can be replaced by that one we did earlier by using mean value theorem. So here, with replacing this term by that one, and we sum now case from 1 to n to get a Riemann sum. So we now, rather than average height, now the same position here, ck, such that this average radius can be written in this way, is good approximation. Now, this is a Riemann sum, and we try to take a limit. When you take a limit, ck will be changed into x, and delta x changes to dx. So here we have a definition. The surface area for revolution about the x-axis, now y equal fx, now non-negative and continuously differentiable over the interval. Then the area of the surface generated by revolving the graph about x-axis is given in this way. 2 pi y and is rotated about x-axis, so the radius must be y. And here we have that, and that is now f of x, y equal f of x in integration. So you can write down here, rather than y, you can put here f of x. And this one is same as square root of 1 plus f prime x squared dx. So we'll use this formula in computation. So here you have to here remember that in this formula, y is used for radius. Okay. Now, if we change the coordinates so that now rotation is about the y-axis, and function is given here x equal g of y, then similarly we can get this formula. In this case, now y-axis rotation, so the x must be radius. Now it's defined on c to d, so the lower bound, upper bound must be c and d respectively, and that's radius, and that's now the curve scaling factor. Now x is same as g of y, so everything must be expressed as a function of y, because you are doing y integration, so that everything must be now here a function of y. Okay. Okay. Here earlier you learned that differential of arc length ds is square root of dx squared plus dy squared, so that integrals in these two equations can be written as in this way. Now that is now S is a to b, 2 pi y, and that portion is ds. And also for this one, that's now from c to d, 2 pi x, that is again ds, so that simply we can write in this way. But practically we use these terms for when we try to get the value, the surface area in computation. Okay, let's go to the example. Find the area of the surface obtained by rotating the curve about x-axis. We are rotating about x-axis, so that the formula we'll use is that one. Now is about x-axis. Now x integration a to b, and here the y will be the radius. So y is f of x, and then we are using that formula. Okay. Okay. So we have to get square root of 1 plus f prime squared. Okay. Now that is y prime equal 3x squared. So that here from this one 1 plus y prime squared is same as 1 plus, now that is 9x to the 4. Right? So here the surface area will be same as integration x is from 0 to 2, and 2 pi, that's y is x cubed, and square root of 1 plus y prime squared, which is 1 plus 9x to the 4, and x directional integration. Okay, for this one, now 2 pi can go out, and then now we can find the antiderivative by using the method of undetermined quotient. Okay, that's half power. So the antiderivative must be 1 plus 9x to the 4, 3 over 2. And we have to put coefficients to get now antiderivative. Okay. And 2 pi is, we'll ignore this portion. And after differentiation of this part, we have to get that one. Okay, of course, evaluation is from 0 to 2. To decide this, the value, we try to differentiate this portion. Then that will be same as 3 over 2. And here, inside the parentheses, the same, and half power times. And that derivative will be now 36, and that is now here x to the 30, right? So that I guess we didn't make any mistake. Okay, so that is a 36x cubed, and that one becomes here 18 times 3. So what is that? That is 81. Okay, that is now 18 times 3. Okay. Okay, we put here 3 times 18. It is 54, in fact. Now, x cubed, and here that 1/2. So extra term is this one. So we have to put here now the quantity, and 1 over 54. Okay. Okay. Now, from this one, you can get quite easily. Yeah, so that there is 27 and pi, and then once it is 2, then that is 16 plus 9, and 6 times 9, so that, okay, let's say in this way, 16 times 9 plus 1 to the, okay, 1 to the here 3 over 2, and once x equals 0, then it will be 1, right? So we got the final answer. You can simplify. Okay, now in this example, we'll try to find the area of the surface obtained by rotating the curve about y-axis. Now its rotation is about y-axis, so that we'll try to use this formula. Now y is moving from c to d, and 2 pi g of y, that is x. So radius must be x, and now here this scaling factor, but everything must be a function of y, okay? Okay, now so that the surface area, okay, for that one equal y integration from 0 to logarithm 2, and then 2 pi x. X must be radius here now, and then square root of 1 plus g prime y and square root dy, right? So we'll try to get that portion first. Okay, that is g of y. So the g prime y, that is same as now 2 on the bottom, the same, and that is e to the y minus and e to the minus y, right? Now 1 plus g prime squared is the same as now here 1 plus, okay, half will go out 1/4, and now e to the y minus e to the minus y squared. So that is same as 1 plus 1/4, and then, okay, that is e to the y squared and plus e to the minus y squared, and then that is minus 2. Okay, we'll put that in. Now, with 1/4, that's the same as minus half. And if we add 1, then it'll become plus half. So that here we can rewrite this one in this way. That is same as the same quarter. And then here e to the y squared plus e to the minus y squared plus 2. Right? But if we are considering only this one, then if it is positive, then we'll get that. So that is the same as now here, and in half on the bottom, and e to the y plus e to the minus y here, that squared. Right? So we apply square root, then here we have that term. Okay, so this integration is same as integral from 0 to logarithm 2, and 2 pi times x is 2 on the bottom. Now e to the y plus e to the minus y. Now that's x, and square root of that one is the same as again this one, so that here we have that squared and dy, right? Okay, that is 1/4, so that that is same as pi over 2 and integral from 0 to logarithm 2, and then that squared, which is same as now e to the 2y plus e to the minus 2y plus here 2. Now for each one, antiderivative is quite easily you can get half of e to the 2y, and there is a minus half of e to the 2y, and now there is 2y. So after getting the antiderivative, and you can evaluate the integral. You can finish it. Okay, here we'll go to another problem. Now for that one, exactly, now we can use the same formula, and y is moving from y to 0 to a over 2. Now that one is in fact now mimicking this one. Here, if you here now square both sides, then x squared will be same as now a squared minus y squared. So that is now equation for a circle of radius a, and then now x is only positive 1 and y is moving over there. So pictorially, right now, here, given in this way, okay, now over there, x is positive, and then here there's a, okay, now among this circle, right now, y is moving from here to over there halfway, now, okay, and x is larger, so y is moving this area, so eventually the curve is this one, that curve, that portion of the curve is rotated about y-axis and surface is made, right? Okay, now we'll try to get here g prime. That is the same as here half will come out, and then here a squared minus y squared and minus half power, and this is minus here 2y, right? Y derivative, so that 1 plus g prime squared will be the same as 1 plus now minus half and 2 cancel to be minus 1, square of minus n is 1, so that now there is y squared, and then now that is a okay, a squared minus y squared and minus 1 power minus 1, which is same as now a squared minus y squared on the bottom, and then that is here a squared minus y squared and plus y squared, so that there's a squared, right? So here we have the surface area is same as integral from 0 to a over 2 and 2 pi, and about y-axis rotation, so must be x, which is same as square root of a squared minus y squared. And now here square root of this term is the same as here now, okay, top will be a and bottom will be square root of here a squared minus y squared, so that we can cancel out these two. Of course, we have to have here dy, and 2 pi a is not constant, so that the same as 2 pi a times now the length is a over 2. Okay, so that's the final answer. Okay, now we have a little bit different formulation. Now curves revolved about the other axis. Here surface is made by rotating y equal fx, a axis moving from a to b, but now that is about revolution is done about y-axis. Okay, we'll go to the earlier one for this one. Now y equal fx, that one, and defined over a to b, is now rotated about the x-axis. But here, we'll try to rotate it about y-axis, even we have y equal f of x. Then in this case, its rotation is about y-axis. And here radius must be x. Because here now, okay, pictorially, we have A to B, a curve is given, and then rotation is about y-axis. And in this case, here, okay, now, even though it is defined from A to B in x-axis, now, because this rotation, the radius must be, surface is made with this rotation, but now, here, the radius must be here, that one, which is x. X is moving from here to there. Now, so that radius must be x, right? Okay, radius is x. So we can write here surface as 2 pi x and ds. And that's considered in this equation, okay, here, okay. Now, ds can be written in this form so that here, even though we are making y-axis rotation, we can get such formula, yet integration is in x direction from A to B, and radius, and that one is now, along with curve scaling factor, we try to get x integration. Similarly, for here x called g over y, and y is moving from C to D, here revolution is now about the x-axis. So in this case, once there is x-axis rotation, then y must be radius. So here we can say that s is same as 2 pi y ds. Now ds can be written in this way, either this way or that way, so that yet we can get the surface area by using here y-directional integration rather than x-directional integration. So that's the formula. Sometimes, now you can change into x-directional integration. However, sometimes it's not easy to get the formula out of this one, because x-axis rotation, out of this one, for example, you can get y equal here f of x, and of course x corresponding lower bound and upper bound of x, so that a and here x like that. But this solve is not easy, so that rather than changing the formula, we try to use it, and then now along the other direction we try to get the integral. That's the idea. Okay, let's go to this example. Now here we want to find the area of the surface obtained by rotating the curve about the x-axis. That one. Here now the second case. In this case, radius is y, and then now we have to get this portion. So let's do it here. Now x prime. So that is x prime. So that means that in fact this is dx over dy, right? Okay. That is same as now here 1/3 is there, and 3 over 2 will come out, and here y squared plus 2 and half power by using chain rule. And now y squared plus 2 must be differentiated, then that is 2y. Okay, here 2 and 2 cancel out, and 33 cancel out, so that is same as y, and here y squared plus 2 half power. Okay, now here 1 plus x prime squared is same as 1 plus that squared, that is y squared, and y squared plus 2. So that is same as y to the 4 plus 2y squared plus 1, which is same as y squared plus 1 squared. Aha, so it is a perfect square. So here, the surface area is same as y is moving 1 to 2, from 1 to 2, and here 2 pi, and because x is rotation, so that y is radius. Let's put it here y, and then here square root of that portion, which is same as now y squared plus 1, and dy here, that is now radius, right? Okay, we'll try to get the integral along with y-directional integration, but everything is a function of y, so that simply you can write here y and stay there, no problem, okay? So from this one, 2 pi, and now integral from 1 to 2, and that is y cubed plus y and dy. Okay. From now on, getting the solution is really a piece of cake. And you can get the antiderivative from this one. Here, quarter x to the 4 plus half y. No. This y to the 4 and y squared. And from 1 to 2, then you will get the answer over there. Okay. Now here, we'll consider the cases curves revolved about the odd axis. Now we'll consider again, and we'll approach this one a little bit different way. Recall the differential of arc length. And earlier we considered that, so that ds is the same as square root of dx squared and dy squared. So we may consider this one as a ratio, but originally it's not a ratio. But if we consider differential, then we can consider this one as a ratio. Now, dx can go out, and here that can be changed into 1, and this one is changed into now dy squared over dx squared. Right? So we can get it. Or you can get dy outside, and then we can get that one. So here we consider a special case. Y equal fx is a monotone function defined on a to b, and we put a is larger than or equal to 0 for simplicity. And now we try to rotate the curve about y-axis, so that now that's okay. To make a rotation about y-axis, we make a is larger than or equal to 0. So that from here to there, the curve is made and monotone, so either increasing or decreasing, to get its inverse. So it's a special case. Now that curve is rotated about y-axis. Then we have a surface, and we'll try to get the area of a surface by using either an x integration and y integration. This surface, that is a to b. Then in y direction, now there is a c2 here, that is now d, so that we can compute this surface area by using x integration and y integration. And in any case, because we rotate the curve about y-axis, the radius must be x. So here, the integration must be 2 pi x ds. Now, ds can be written here in x-directional the format, and scaling factor, curve scaling factor, and dx, and y-directional format, and dy. And in this case, rather than x, we are using g of y, the inverse of f. And that way, we can get the integration. Here, f and g is inverse of f. It's a monotone so that you can get it. That means that the inverse can be gotten by solving for x so that g can be determined. It's a special case, but along this claim, you can understand the ds, the meaning of ds, and it can be used this way or that way. And once you are using this way, then now in integration, lower bound, upper bound is 4x. And now for that one, you have to find the corresponding lower and upper bounds for y. Okay, let's see this example. Find the area of a surface obtained by rotating the curve. X is now square root of 4 minus y. Y is moving from 0 to 4. Now that is about y-axis. Rotation is about y-axis. Okay, let's try to visualize it here. Okay, now, here, and if y is 0, then that is length 2 here. And if y is 4, that is 4, then the value is 0, so that it is given in this way. Okay, let's try to make a curve a little bit better. My hand is shaking a little bit. Again. Anyway, that's curve. We made a rotation about y-axis. So the surface was made now for that one. And here, if we want to get x integration, then now this is a form of right now x equal g of y. From this one, you have to get y equal f of x format if we want to get x integration. So let's do that. And here, square, then x squared equal 4 minus y. From this one, y equal 4 minus x squared, right? So that now we have to get that one, 1 plus f prime. That's now f of x, f prime squared. So that y prime equals same as here minus 2x. So from this one, 1 plus y prime squared equal same as now 1 plus 4x squared. Right? Okay. Okay. From here, the surface area is same as, now x is moving from 0 to 2. So that from 0 to 2, and then x direction integration, so that 2 pi, and we have x, and then now 1 plus y prime squared. So the square root of 1 plus 4x squared, right? And dx. From this one, 2 pi is there. And then for that portion, let's try to find antiderivative. We'll have a coefficient. And then there must be 1 plus 4x squared and power 3 over 2. Of course, evaluation must be from 0 to 2. We have to decide this coefficient. Okay, let's do it. We differentiate this one, then 3 over 2, and the parentheses, the same thing, and power 1/2. Then the derivative of the inside here, that will make 8x. Right? Okay, that will make 12, and here half power of this amount, and then x. So we have extra 12. So we have to put here 1 over 12. Okay. Now from this one, and that is now pi over 6, and then Once it's 2, then that is 4 and 16, 17. 17, 3 over 2, that is 17 square root of 17. Once x equals 0, which is 1. Okay, we get this one. So when we are working on x integration, then we get this value. How about y integration? And y integration, we are using that one. Okay. So now, originally is given x called GY format, so that now that GY prime and squared and add 1, we'll do that. Okay. G prime, that same as half power, so this half will come out and 4 minus y and minus half power, and here minus 1. Right? Okay, so if we are trying to get 1 plus g prime squared, then that is same as 1 plus now 1/4, and then on the bottom that's squared, so that is same as 1 over and 4 minus y. Right? Okay. So that is the same as, okay, we put here 4 minus y, and then this is 16 minus 4y plus 1, so that's 17 minus 4y. Okay. So we have, from this one, now surface integral must be from 0 to, now we are working on y integration. Y is moving from 0 to 4, and yet the radius must be x, so that here 2 pi, now, but we have to get y integration, x must be replaced by that quantity, and that is square root of 4 minus y. Okay, this term came from here equal x, the radius, right? Okay, and then we have to put that portion, which is the same as now here by taking square root we have here. Okay, that will be half, and that portion will be here on the bottom, 4 minus y, and again that one will be here square root of here 17 minus 4y. Right? This will cancel out half and 2, so that eventually we have here pi comes out, and from 0 to 4 and square root of 17 minus 4y and dy. Okay. Now for this one here, pi n, okay, antiderivative will be a coefficient times here, that is 17 minus 4y power 3 over 2, and evaluation is from 0 to 4, right? Okay, now we have to find this coefficient, okay, from here. Now 3 over 2 will come out, and here inside of parentheses the same, and half power, and here derivative of this term is same as minus 4. So that extra term is the same as minus 6, right? That is a minus 6, so that we have to put here 1 over minus 6. Okay, so that is now minus pi over 6, and then we'll try to evaluate this one. Once x is 4, then it's 1, so that 1 minus. Once x equals 0, then 17, so that 17 power 3 over 2, which is 17 square root of 17. right? Now you'll see the same result, right? So that sometimes the rotation is about the other axis. However, here the beauty of this mathematics is that here, now once you decide the radius, right, and for this ds, you can solve this, you can express this ds either this way or that way, about x, about y. You can do it so that you can get the right answer even though you integrate the other direction. Okay? That's the end of the section. Thank you.